So in this video, we're going to talk a little bit more about one-sided limits. So we already kind of alluded to this idea of approaching a, as x approaches a number from the left side versus approaching the number from the right side. So we define this idea by what we call a one-sided limit. Okay, so first let's just kind of look graphically again at what we mean by this. I'll actually draw the graph this time. And then we'll look at some more graphs on the graphing calculator as well. So let's say we have this graph and we just have this line, and let's say we have this point and this is some number a, right? So we can talk about the limit as x approaches a of f of x. So we'll say this line is f of x, right? And we basically have two directions we can approach it from. And this is kind of a consequence of our two-dimensional graphing system, right? We can approach it from the left side, and we can approach it from the right side. So in other words, we can look at the values where x is less than a and the values where x is greater than a. So in this instance, with this graph that I drew right here, it's pretty clear that it's approaching the same number from the left and the right sides. But this doesn't have to be the case. If we go back and look at an example we previously looked at, so the absolute value of x minus 2 divided by x minus 2, which is going to be 1 if x is greater than 2, and negative 1 if x is less than 2. So we can see that if we're looking at the limit as x approaches 2 from the left side, in other words, we're looking at the numbers where x is less than 2, we can see that the limit would be, in this case, negative 1. And then if we look at it from the right side, we see the limit would be 1. So again, the limit is, what does this function look like it's approaching? It's a constant function on both sides. So it looks like it's approaching, the number that all of the other numbers correspond to, right? Namely 1 on this side and negative 1 on this side. So we would say that the left-hand limit, or the left-sided limit of as x approaches 2 in this case, is negative 1. And then the right-hand limit, or the right-sided limit, is as x approaches 2 is 1. So the way that we're going to write this, okay, and let's go ahead and I'll just bring this graph onto here so that we can use it. So this is 1, this is negative 1, this is 2. So we have this line right here and this line right here. Okay. So we let f of x be the absolute value of x minus 2 divided by x minus 2. So we would say that the limit as x approaches 2, and then to signify that we're going only from the left side, we put a little negative sign right here. So kind of as a superscript. So we say the limit as x approaches 2 from the left, because what we're saying is it's like from the negative side. It would make more sense if it's centered at, if it's the limit as x approaches 0. That's kind of where the notation comes from, but we just use it for any number. So it's like from the negative side is kind of what we're saying. So as x approaches 2 from the left side of f of x is negative 1 in this case. And then the limit as x approaches 2 from the right side, we use a positive number, or a positive sign, a plus sign, to signify from the right side. The limit as x approaches 2 from the right side then is going to be positive 1. So if you remember our original definition of the limit of f of x as x approaches 2 should be one number. So how do we kind of reconcile this, right? Where we have the limit going into two different numbers, depending on which side you look at. And we actually already said that we would say that in this case, the limit does not exist, right? So let's actually write this down as a rule now. Okay, so the way we could write this is that the limit as x approaches a of f of x equals L if and only if the limit as x approaches a from the left of f of x equals L and the limit as x approaches a from the right of f of x equals L. So if and only if, this statement means that this side implies this side and this side implies this side, right? So in other words, they're logically equivalent. So if you know the limit as x approaches a of f of x equals L, then that tells you that the two-sided limits are both equal to L, or the one-sided limits are both equal to L. And if you know the one-sided limits are both equal to L, then that tells you that the limit overall is equal to L. So the one-sided limits need to be going to the same number in order for the limit to exist. Okay. So we could say like a corollary to this would be, so if the limit as x approaches a from the left of f of x does not equal the limit as x approaches a from the right of f of x, then the limit does not exist, right? And we write that as DNE. That's a common abbreviation for does not exist. And to be more precise, they both need to be equal to some finite number. As we talked about, if it's infinite, we still say it doesn't exist, but we might write infinity down even though it still doesn't exist, right? So there's more cases where it might not exist. So let's just look at a simple example where, the limit will exist because the one-sided limits are the same thing. So if we just look at something like the limit as x approaches 0 of x squared, maybe, right? So we should be familiar with the x squared graph by now. So I'll just draw a quick sketch of it. Not very precise, but it has its vertex at 0, 0, right? So we would expect the limit of this function as x approaches 0 to be 0, right? Because that's where the function is going. It happens to be the output on this function as well, at 0. So we would want to show that the limit as x approaches 0 from the left side is equal to 0, and from the right side is equal to 0. And here, it's easy enough just to do from the graph here, right? We can see that as we approach it from the left over here, it's clearly going to 0. And from the right, it's also clearly going to 0. You could also make a table if you wanted to, like we were doing before, to show that the values are getting closer and closer to 0. So in a lot of cases, we don't necessarily need to show it for both of them because it might be clear that they're going to the same value, but we need to be careful of the cases where they're not going to the same value, like this one, for example. So in this case, there would be no limit as x approaches 2.